This video is over section 8.6 titled Numerical Integration. Specifically in this section, we are going to talk about different types of approximations. We'll talk about the trapezoidal rule as well as Simpson's rule. And the reason these are helpful is because sometimes there are functions that you want to integrate, but the antiderivative cannot be found. So you can still apply the fundamental theorem of calculus, but it takes a lot of work. So sometimes for different functions, like the ones listed here, it's easier to apply some sort of approximation technique to approximate the integral rather than evaluating the integral. So the first type of approximation method is by using trapezoids. And hopefully you can remember how to find the area of a trapezoid, but if not, I'll talk about that shortly. But basically what we'll do is we'll have we'll have some amount of trapezoids in some region, and we will add all of those trapezoids together. And one thing that I want you to notice is that some trapezoids share a side, and that's going to become helpful when we look at this formula for the trapezoidal rule. So the next few slides just kind of show you how the trapezoidal rule is developed, and you can take some time and read through all of that information. I'm just going to try to make this video efficient by showing you some examples. So here is basically how the trapezoidal rule is developed. I want to remind you how to find the area of a trapezoid. Oops. The area of a trapezoid is found by taking a plus b divided by 2 times the height. You can also think of this as 1/2 of the sum of the bases times the height of the trapezoid, which is the distance between the two parallel bases. Okay, so you can take a look at this diagram, but what it leads to is the following. So if we have n trapezoids, what happens is we end up with this formula here. Okay, this gives you the height essentially, and everything is divided by 2, and so that 2 is factored out. And then if you look at this, you have some repeats, and those repeats are doubled. Okay, and that was illustrated on one of the first few slides. Okay, so moving on, we know that if we have an infinite number of trapezoids, I'll have a better approximation. So that's why this limit is approaching infinity. And remember that when the limit approaches infinity, then we end up with an integral. So the trapezoidal rule can be summarized here. So it's important to notice that the function must be continuous on an interval, and it's used for approximating this integral. And here's the formula in which you will follow. Okay, so this is something you'll want to refer back to. N is the number of trapezoids. And I will just jump into an example. In this example, we want to use the trapezoidal rule to approximate the value of the definite integral for the given value of n. So In this case, I've provided a graph for you, and it's helpful to just focus on the interval in which we're interested, which is from 1 to 2. And if I look at this, I want to split this up into 4 separate regions. So this is what I have here. I have these trapezoids, and I want to find the area of each of those trapezoids essentially and add them together to get this approximation. Now, it's helpful to find the width of each of those trapezoids. The width of the trapezoids will end up being a 4th. Okay, so you can find that by taking b minus a over n. b minus a is the interval, so 2 minus 1 over 4 gives us 1/4. So this is the width of the intervals, but you can kind of see that here. If this is 1, then this is going to be 1 1/4, 1 1/2, and then 1 3/4. Okay, but let's approximate this. So remember, we are approximating this integral. And this is going to be approximated by the trapezoidal rule, which is this. So in this case, this is what we'll be using. Sorry, I have run out of room. All right, so this is the height of x sub 0, and then x sub 2, or I'm sorry, x sub 1 is shared here and here. So that's why that height is doubled. Same for this height and this height. So 3 of them are doubled in this case. All right, so what I want you to remember that this notation is the height. So what I want to do is find the height for here, here, and so on and so forth. So essentially what I'm doing is the following. This simplifies to 1/8, and then I want to find f of 1. Because x sub 0 is 1, we start off with 1. And then f of 1 1/4, and f of 1 1/2, and f of 1 3/4, and f of 2. Okay, you'll end up with one more term than the number of trapezoids, FYI. And all we are doing is finding these heights. And the way we find these heights is we plug this x value into this function. So all we're doing is plugging these in here. So when we do, I'll have 1/8 times. When I plug 1 in, I get 1/4 plus 1, which is 5/4, plus 2 times. So I'm going to plug 1 1/4 in here. So I'm plugging in 5/4 plus 1 over, oops, sorry, this is over 4. So on and so forth. Okay, so I'm just plugging in this value in for x. Okay, so after some simplifying, I end up with 1/8, and you should get 5/4 plus 89 over 32 plus 25 over 8 plus 113 over 32 plus 2. Plug this into your calculator, and you end up with the fraction 203 over 128, which is approximately 1.58593, so on and so forth. Okay. So that's using the trapezoidal rule to make this approximation. So the area under this curve from 1 to 2 is approximately 1.5859, so on and so forth. The trapezoidal rule is one method to approximating. Simpson's rule is another method of approximating. And you can see here that the subintervals in a trapezoidal rule, you can approximate f by first degree polynomials, whereas Simpson's rule, you can take it a bit further. It's a little more advanced, and you can approximate by second degree polynomials. I'll let you kind of pause this and kind of read through a couple different things. Again, I'm just going to skim through how it is derived and show you some examples of how to use it. One thing to pay attention to is that in Simpson's rule, n must be even. So whatever the different partitions are, it has to be an even number in order to apply Simpson's rule. Here is just a little example. When you are choosing things, it has to be an even number. Here it kind of illustrates the theorem that was shown previously, that 8.4 theorem. Kind of shows you what happens when you integrate a polynomial. And here is the theorem that states Simpson's rule. And again, this is simply an approximation. N has to be even, which we have talked about, and we're just going to be approximating this integral, just like the previous example. So here, a couple things to notice is this is the formula that you'll use. And there are a couple differences with a coefficient of 4 and 2 alternating. And instead of 2n in the denominator, you will have 3n. So what I'm going to do is I'm going to show you how to use Simpson's rule on the exact same example. Now, in the previous example, we had the graph given to you. And what we're going to do is group this. So we are going to integrate from 1 to 2. And then this here is half of it. So what we're going to do is group these. So this is a group, and then this is a group, where this is 5/4 or 1 1/4, and this is 7/4 or 1 3/4. Okay. So the formula is as follows. This integral will be approximately b minus a over 3n times f of x sub 0 plus 4 times f of x sub 1 plus 2 times f sub x plus f of x sub 2. And we're just alternating. In the last term, in the first term, have a coefficient of 1. Okay, and again, if n equals 4, you are going to end up with n plus 1 terms here. Okay, so we're just going to plug everything in. B minus a, again, is the interval, so I have 2 minus 1 over 3 times 4. Then x sub 0 is 1, x sub 1 is 5/4, so on and so forth. So I'm just going to fill that in now. And when you are completing this homework, you certainly don't need to show all of these steps if you don't want. I'm just showing you for illustration purposes. All right. So then, just like before, these values here are x values, and we are going to plug them into this formula here. So I'm going to plug 1 in for x, I'll plug 5/4 in for x, 3/2, so on and so forth. So when all is said and done, I end up with 1/12. You'll get 5/4 plus 89/16 plus 25/8 plus 113/16 plus 2. Adding those together, it simplifies to 19. So this is 19/12, which is approximately 1.583 repeating. Okay, so we have found that applying Simpson's rule to approximate this integral, we get this. So what we want to do on the next slide is make some comparisons. So we found the following results. Using the trapezoidal rule, our approximation was 1.58593. Simpson's rule gave us an approximation of 1.58333, so on and so forth. Now, if I want to find the exact value of this integral, I can just throw this into my calculator real quick and make this approximation, or I can apply the fundamental theorem of calculus to get the following approximation. This is equal to 1.5833. Okay, so if this is the exact value of the integral, look how close these approximations are. It's quite impressive, if you ask me. Now, sometimes it's helpful to know what to expect as far as how close of an approximation you may have. So there's a way to identify the error in each of the approximation rules, and those formulas are here. So if you want to find the error in the trapezoidal rule, you will apply this formula. If you want to find the error in Simpson's rule, you will apply this formula. And basically, it will tell you when you are approximating how close your result will be. So here it kind of tells you a little bit about what this theorem states and just some different results that could happen. Go ahead and pause and read through this. There's no need for me to read it to you. But instead, I'm going to show you some examples. So it says, use the error formulas to estimate the error in approximating the integral given with n equals 4. And we will do both the trapezoidal rule and Simpson's rule. So on this slide, we'll focus on the trapezoidal rule. So if you look at the formula says that the error is going to be less than or equal to the following: b minus a cubed over 12n squared times the maximum of whatever the second derivative is, that absolute value, where a and b are is the interval. Okay, so if this here is the formula, this tells me I need to find the second derivative. Okay, so I'm going to say that f of x is 2x cubed. If f of x is 2x cubed, then f prime of x is 6x squared, and f double prime, I'm sorry, this is double prime, is 12x. Okay, so applying this formula then, e is less than or equal to, this is essentially the interval, 3 minus 1 quantity cubed, over 12 times n. It tells us n is equal to 4, and we'll square that. Now, the maximum of this absolute value means if you plug in a value here, what will provide, like in that interval, what will provide you the greatest result? Well, that will occur when x is 3, okay, the biggest value on the interval. So I'm going to multiply this by this, so it's essentially f double prime of 3. And f double prime of 3 is found by taking 12 times 3. So e is less than or equal to, pardon me, 8 over 192 times 36. When I multiply that out, I get the error to be less than 1.5. So when applying the trapezoidal rule with 4 trapezoids, to approximate this integral, I will have a value that is less than or equal to a difference of 1.5. Now you'll find in the next example, when applying Simpson's rule, that we will get a better approximation. So this is the exact same problem, but now we are going to find the error with Simpson's rule. So this formula from one of the previous slides is the following. Here we want to find the maximum value of the fourth derivative. Okay, so we need to find the fourth derivative. In the previous example, we found that f double prime is 12x. So triple prime is 12, and the fourth derivative, is simply 0. So plugging into the formula, we have 3 minus 1 to the power of 5 over 180 times 4 to the fourth times the maximum of the fourth derivative. Now, no matter what I plug in for x into the fourth derivative, the outcome is 0, no matter what. So this is 0. And it doesn't even matter what this simplifies to, because anything times 0 is 0. Which means if I apply Simpson's rule to make this approximation, I will have no error. It will be spot on. The approximation ends up giving you the exact value in this case. This concludes section 8.7.